My name's Lester. I work with the Vespa team at Verizon Media, primarily with machine learning technologies and so on. First of all, just want to know, how many of you heard about Vespa before? And if I don't mean the like two-wheeled moped? Okay. How many of you actually tried Vespa? Okay. One. See if we can do it better. Okay, so I'm here to talk to you. I'll get back to Vespa a little bit later, but first I'm going to talk a little bit about the kind of fun project we did about ranking article comments. And with article comments, I mean, of course, those comment sections that you find all over different websites, like typically news sites and so on. So this is an example from Yahoo.com, which is a fairly active community around these news sites, these comments. And the idea with having these kind of article or comments or comment sections at all is to drive user engagement, right? Because that can be monetized. Because people that engage probably stay longer at the websites and can get more ad impressions, and hopefully they click on some ads and so on. The only problem with that, of course, is that most comments are crap. They're garbage. They're bad. They're really, really bad. I mean, there can be comments that really don't bring anything to the discussion. They can be attempts at bad humor. They can be personal attacks. That's okay, right? People are people. But there's some type of comments that are not okay, right? And then, like hate speech, racist slurs, toxic comments, death threats, and so on. So those are comments that we really don't want to show, possibly. But there are some really good comments as well, right? Comments that bring something to the discussion, probably add something to the article that they are commenting on. Comments that pique your interests, maybe pique your curiosity in some way. And those are the kind of articles that we want to show. So when building a community, maybe those kind of good comments, the interesting comments, those are ones that we want to kind of, float up to the top a little bit. And those bad comments, I mean, those really bad comments that obviously violate some sort of terms of service on, we want to probably delete them. But those really bad comments, we want to kind of sink them to the lower part. So building a community around this is kind of like it is a ranking problem, right? So we need to kind of float these interesting comments up and these bad comments down. Problem is we don't really know how to define interestingness, right? So we need to kind of put some sort of algorithm. We can't write an algorithm to do this. So we want to kind of approach this problem with the machine learning approach. And something that evolves over time, that follows the community, follows the kind of movements of what's going on. So we're going to do that using a reinforcement learning approach. So first of all, for those of you who haven't heard about Verizon Media is an organization that was rebranded earlier this year from Oath. Oath was the merging of Yahoo and AOL when Verizon bought Yahoo a couple years ago. And basically, we function as a technology provider towards a host of different websites and also into the Verizon group. Vespa comes from Yahoo. It is basically an acronym for Vertical Search Platform Architecture. And as such, it's been developed over many years inside Yahoo, and it's always been a very popular product there. It's used in hundreds of applications, and it's in heavy use. So it serves over 1 billion active users every month. Hundreds of thousands of queries are running at any given time, over billions of content items. And just some small examples of what it's used for. So we have there Flickr image search. The front page of Yahoo, almost all the kind of components that you see on Yahoo front page is served by Vespa in some way. So for instance, we have a personalized article recommendations, the news kind of stream, personalized. Also, Vespa is powering the 3rd largest ad network in the world, after Google and Facebook, obviously. So there's an example of a personalized native ad. And Vespa handles things such as real-time bidding and so on in that case. And the system that we are going to talk about today is the commentaries or comment sections where we use neural networks and reinforcement learning to train this model. Okay, so the Vespa team, we're a team that's situated in Trondheim in Norway. We're about around 30 developers full-time working on the core system there. The kind of one of the good things about our setup is that we own the entire stack of the system, right? So, I mean, not anything against Lucene and Solar and Elasticsearch and so on, but we own the entire stack of the solution, meaning that whenever we can be a little bit more agile when it comes to adding new features and so on. The history of our team really started way back in 1998, or probably even before that, during the search engine wars. So we were, the kind of predecessor to Vespa was powering all the web.com. It got split out in 2004. One part went to Microsoft, one part went to Yahoo via Overture. And as I mentioned previously, in 2017, Verizon bought Yahoo, we got Oath, and then now Verizon Media Group. One thing that we're really proud of is that we open sourced Vespa a couple years ago, and we're now in the process of trying to build some community around this. Okay, back to the talk of today. On different sites inside of Yahoo, on different properties such as Yahoo Finance, Yahoo News, and Yahoo Sports, we've had these commentary sections for a while now. We have this kind of baseline, this existing solution, which kind of sets a little bit parameters of the solution that we're trying to build. And it's a fairly active community, as I mentioned previously. So we have about 1 billion different comments across these different sites, running around 12,000 queries each second, and twice that for updates. Updates is like, upvote or downvote and so on for comments. And some of these comments can have, or articles can have a lot of comments, such as 100,000 comments or more. And based on this existing solution, we know that this kind of article section or comment sections, they really drive engagement. We can calculate a dollar amount per year of how much of a value it is for a person that regularly writes comments and people that regularly view comments and so on. So it's a important section of these different sites that we have. This existing solution uses a set of features to do what it does, and when we're looking at a new solution, then we need to look at what kind of features we can use. And the regular features that you use in these kind of community sections is the community features, or how the users interacted with the comments, like upvotes and downvotes and replies and so on. And there's many ways you can do that, such as upvotes minus downvotes, or a fraction of upvotes related to the total number of votes. What's more in use probably is this Wilson score, which is more like a statistical sampling used in sites like, well, at least to be used in sites like Reddit. I don't know if it's now or not, but it's more like a confidence interval based approach on upvotes or downvotes. Community features. So we bundle these together, upvotes and downvotes, inside this Wilson score, which is a feature. Comment level features could be like relevance to the topic. For instance, we use a kind of a semantic representation of the article and each comment as well. And other features we can use is moderation, level features, such as this one from Google. Has this perspective API, which works as a kind of convolutional neural network. You just send in some text, I think it's an open API, and you get a score back. Obviously, this is a fairly toxic comment. Other features we can use, authors, the reputation of authors, so authors that have consistently got good feedback on their comments, such as a lot of upvotes and a lot of replies. We're also experimenting with personalized comment ranking, if a user has kind of consistently upvoted another user's comments and so on. And other features such as time, freshness, and so on. There are different features that we can use in building a solution. And the previous ranking algorithm that was used is very kind of simplistic. Basically, you have all the features that we have, and we use a kind of linear weighting towards these, and hard-coded as well. And obviously, this is what we want to improve. Right? We need to come up with some way of weighting these different features differently. But it did its job, really. But we're going to do better. So in working towards a new solution, we have to we can take a step back and ask a few questions and how we can kind of, do better. And there are three different kind of aspects here. One is the scoring. Each comment gets a certain score that we rank based on. And obviously the previous solution was this kind of hard-coded linear weighting. Ranking. Previous solution basically just ranked these comments in decreasing order of the score. And learning, previous solution didn't really do any learning, at least not in builds. You could use some sort of like A/B testing and come up with different features manually and so on. But A/B testing is very slow. I mean, you need at least a couple of days, maybe a week to get a statistically significant answer and so on. So, iterations take a long time. So we can ask some questions on how we can do this a little bit better. So how should features be combined intelligently? So we would like some sort of kind of model or anything that can combine these features, maybe capture these nonlinear relationships between these features and so on, and learn them by itself. So ideally, this Wilson score that I showed, this system should be able to figure out that's the kind of best feature to use by itself. And we would use a kind of neural network, kind of fits the bill for that. For ranking, if we are using a neural network to score these things, right? If you want to train a neural network, then we need some sort of labels, right, usually. So for each kind of input to the neural network, we get some labels, and we can use some sort of function or loss function to train these networks. However, we can't really do that with comments, right? Because we don't show users one comment at a time and get feedback on them. Now we show them a list of comments, right? And the problem with that is that no user kind of, goes all the way to the bottom of the lists. So, and different users have different levels of abandonment. They stop reading these comments after a while. And so each kind of label that we can infer from this ranking list obviously has a pretty hefty position bias. And the way that we kind of overcome that is that we use sampling, importance weight sampling, with built-in exploration. I'll get back to a little bit later with details. Learning as well, I think I mentioned previously, is that we would want a system that would be able to learn directly from user feedback, from raw instrumentation, if possible, and keep updating the model over time. And we settle on using reinforcement with dwell time rewards. Dwell time is the kind of total time spent reading these comments. And that's the kind of like our optimization target. We want to increase the time spent on this. So, just a little step back, talking about reinforcement learning in general. I guess most of you have some idea of what that is. Reinforcement learning is a little bit different than supervised learning and unsupervised learning. So we're supervised and unsupervised learning are more like statistical techniques to learn some sort of model based on the data. And I like to think of reinforcement learning as a little bit more, AI-ish. So the premise of reinforcement learning, of course, is that we have some sort of agent that is put inside some environment, and this environment kind of generates inputs to this agent, and this agent chooses actions that has some effect on the environment, and this goes around in a loop. Once in a while, the environment produces some sort of reward, which is an input to the agent that it's been doing something good or something bad, right? And the problem is that this reward can be very sparse. So if you have, for instance, a game-playing agent that plays chess, then obviously the only reward that you get is all the way at the end of the game. Did you win or did you lose? And if you've been playing like 100 moves to get at that state, then it's kind of difficult to kind of propagate that signal back to say which of the moves we're defining in this win or this loss. That's called the credit assignment problem. If we remove the credit assignment problem, in that we always get a reward based on the action, this is reduced to a problem called contextual bandits. Contextual bandits is like an extension of the multi-arm bandit problem. Probably familiar with that one. The metaphor there is that you have a possibly large number of different, these slot machines, these one-armed bandits. Each of them has a different payout. And your task is to maximize your payout based on the number of trials. So the point is that you have to kind of go through and explore which of these machines give you a better payout, and you have to exploit this information. So this exploration-exploitation dilemma. Contextual bandits kind of expand upon this. With each of these kind of metaphorical machines, you have some side information or context that you can use to kind of choose these different slot machines, if you will. And that gives itself to the problem up here. The context is really just a feature vector. And based on this feature vector, or feature matrix, or high order relationships, you choose an action. And the process of choosing an action from a set of features is called a policy. And usually, this policy involves calculating some sort of score for each of these different kind of arms, and using that kind of score to choose an action. So if you had a policy that always chooses the most kind of the highly scored action, that would be an exploitative policy. While an action or a policy that chooses at random would be a explorative policy. Usually you want to do something in between. Now you would think that since we always get reward directly based on an action, then you could use some sort of supervised learning problem, right? But you can't, because the reward that you get back is conditioned on the chosen action. What that means is that you kind of choose an action, you get a reward back, so that's okay, but you don't know which reward you could have gotten if you choose one of the other actions, right? So you need to have this kind of form of exploration and exploitation built in your algorithm somewhere. And the canonical example of this in use in websites is ad serving, right? So basically, here the web page and the user browsing this web page, they form the context, right? And the different ads that you can choose to place on this web page, they're the different kind of machines that you can pull on. Those are the actions that you can choose. And the system over time would be able to choose the best ad to show on this page given these contexts and so on. This can quite simply be extended to ranking, sometimes called contextual semi-bandits. And the same thing here is that you have this feature, a feature matrix, a feature vector, and so on. But this time the policy doesn't choose kind of a single action, but it chooses a ordering of these rankings. Okay, so or ordering of these actions, also called a ranking. And the problem there is that users they don't interact with the entire list, the entire set of rankings, but typically only with the top set of features or actions in this ranking. So we need to use some sort of importance-weighted sampling so that we can construct unbiased estimate for reward. So if we know the probability of these different rankings, we can use that to calculate unbiased estimates. That's what we use for learning. Okay, so if you go begin to become a little bit more concrete, So if you look at the system that we're trying to make, we start with a comment. We want to give that a score. And we have all these features for this comment: community features, comment, author, usage, and time-based features. We construct this neural network, which is parameterized by theta, the parameters, and this gives us a positive score. Right? So that's quite simply how we score each comment. For ranking, then we have obviously a set of comments that are associated with this article, and each of them get their own scores. And what we do is we use an importance-weighted sampling technique here. So first of all, we just kind of collect all these different scores for each of these comments, normalize them, and we use this to select or sample a comment and put that in the first place. So it's not such so that the highest ranked or highest scored comment will get the first spot. It's just it has a much higher probability of actually getting the first spot, right? So that's why we call it importance-weighted sampling. And we do this again. We do sampling without replacement. We remove the comment or the features of the comment that we just ranked, and we do this again. Okay. And select the next one. Now this one did not have the next highest score, so okay, that was chosen. And we go on till we have selected all the comments that we have inside the system, and we now have a ranking. Right? The policy has given us a ranking, and this is random, right? But mostly the best comments are usually on top, and the worst ones are at bottom. But there is a chance that this kind of gets moved around a little bit, and that's important for us to be able to train this system. So in learning, what we do is we have our model, we have our parameters. This gives us different rankings, right? These are the kind of randomly generated rankings that we get. We send them out in the world, and we collect rewards, right, for different users. And as I mentioned, the reward that we use is dwell time, or the total time spent. And if we have the reward and we have the other things, then we can start calculating an ascent, right? Because we want to increase the reward, so we do steps of gradient ascent. And we do gradient ascent in the direction of the expected reward that we have. So if this is a kind of a hypothetical kind of reward landscape for this model, theta, then we can start somewhere in this kind of landscape, and we can take steps along this gradient and hopefully get to the top of the mountain over there, which is the kind of best solution that we can have. Obviously, this is very simplified. Reward landscapes don't look as simple as this, but still, this is the theory. To do that, we need to be able to calculate the direction of expected reward. I'm not going to go through the math too much here, but we use a technique called the policy gradient to come at a very, or somewhat simple solution, which is seen down there. And the important part here is that we have an expression based on two kind of components here. One is the gradient part, and the other is the reward part. And the point here is that the direction of expected reward is independent from the reward itself, meaning that we can choose any type of reward, because since the reward is not inside the gradient, we don't have to take the derivative of that to calculate this and so on. We can use any type of reward that we want, discontinuous, discrete, and so on. And the also nice thing is that we can kind of change our mind based on rewards as well. So right now, while we're using dwell time as a reward, then this can change over time. We don't have to calculate that inside of our model update. Obviously, this is based on this sampling method that is used and so on. It's kind of like mathy a little bit, sorry for that. The more intuitive explanation for this is that if you have these different forms of rankings, then we have these comments that are consistently up on top of these different rankings, and they give higher than average rewards, then the position of the comment inside this ranking, that's the direction of the expected reward, but the reward itself just says how much along this gradient should we actually step. So if it's a higher than average reward, it will give a positive reinforcement. But if it's lower than average time spent on this ranking, then it will be a negative, and thus that will be kind of moved down. So, if usually when we train these neural networks, we start with kind of random weights initialized to some way. But of course, random rankings wouldn't be very good from a user point of view. So luckily, we had an existing solution, and we start training this neural network to emulate the previous ranking using a rank correlation coefficient, Kendall's tau. And this allows us to kind of bootstrap the solution up to a good state before we let it out into the wild. The other thing that's worth mentioning is that we want to do this. This is a reinforcement learning. We're training the model all the time. Things can happen. Could be we have a worse model and so on in one iteration before we get a better one. And then we need to be able to test this model. And we don't really want to test this model by sending it out into wild and monitoring this and so on. So we can use off-policy evaluation. So if we log the features that were used to make a decision, the action that was chosen, which is the ranking, the reward that was given, which is the dwell time, and the probability of this kind of ranking, then we can use something called inverse propensity scoring to be able to kind of give a kind of indication of how good this new ranking is based on logging the old features and so on. This is very important for testing and sanity testing and so on. So that's the theory. Let's go back to building a system based on this. So we need a system that takes these different comments that we have. We have our scoring model and is able to produce rankings based on this. This is something that needs to be done real time, right? Because we have a large amount of traffic, we can't cache this solution. So this needs to be done on the fly always. We send this ranking out into the world, typically some web page. We have some web page that is instrumented with JavaScript and so on to capture reward and so on. And this reward is sent to some sort of distributed database. Very important is that when this ranking is produced to the user, that's when we need to log the features and the action chosen and the probability for that action. And these are two different data streams because this reward happens at a different time point than the actual ranking was produced. So if you didn't log this at the time of ranking, then different features could have changed in the meantime before these were actually sent to a distributed database. So these need to be ranked or logged at different points in time. Let's see, done in the distributed database there, it needs to join these different streams of data, and we can send that to machine learning to perform this gradient ascent step that we saw earlier. And this needs to be run regularly. And the solution that was landed upon is this. Very simplistic, Vespa in the middle there that performs all of these tasks there. So we have a user which has kind of a presentation, a web page. Is viewing these different comments. You can create comments and so on. That goes through comment processing. These are fed to Vespa, which is the database for all the comments. When the user kind of upvotes or downvotes to different comments, that is a update, which is sent directly into Vespa. And then the rewards sent directly to a Hadoop cluster that we have internally. Whenever Vespa produces these rankings, it does also the same thing as with logging. It logs these features and actions and probability to this Hadoop cluster. Once every hour or so, we have a batch job that takes these values and produces a new model, does this testing, it's inverse propensity scoring testing. And if that passes, this new model is just pushed directly to Vespa and made ready immediately. So this is a loop that goes on every hour or so. So for users that don't know Vespa, it's something we call the big data online or big data query engine, open source. And it is a platform for low latency computations over large evolving data sets. And it has a set of features that are very nice for this use case. And one is the advanced relevance scoring with tensors as first-class citizens. meaning that it's really easy to do relevant scoring with tensors. A zero-order tensor is a scalar, a first-order tensor is a vector, a second-order tensor is a matrix, and so on. So those are highly optimized citizens to use in ranking. It's scalable and fast. For instance, I think it was just before the weekend, we did a quick performance test with the semantic search, Elasticsearch versus Vespa. Vespa was 5 times faster or something. Just putting that out there. As a comment serving system, then it checks off all the kind of points that we need. So it's scalable and fast. It's very easy to maintain this level of traffic. Even after, with this neural network scoring this, it does easily 10,000 comments ranking in less than 7 milliseconds, with a very short write latency as well. And there's some other features that are really nice, and that is the direct deployment of machine learning scoring models, which means you can directly take the TensorFlow model and deploy it directly in Vespa and use that as scoring or in ranking. It has advanced computation framework, this relevance scoring for complex features. So for instance, it's simple to take different tensors and multiply them together for use as a feature for a machine learning model as well. So we can kind of string together different models from different vendors as well. We support TensorFlow, Onyx, XGBoost, and so on, and they can be kind of combined together in different ways. It's easy to add your own kind of logic for implementing sampling and logging, which was done here. This is the Java code. And inside of Vespa, or inside of Yahoo, well, Verizon Media, it's difficult to say that. We're kind of still Yahoo. We have a hosted solution for simpler architecture, meaning that we have a system where developers inside of Verizon Media can very simply deploy their applications, and we have 4 releases or so every week, and all these applications are automatically updated and upgraded and so on. So it's very easy for them to maintain or host these solutions. We also have something coming up very soon, which is the same capability for public customers as well. So if you want to try this out, Vespa AI/cloud. Very quickly, one of the reasons Vespa does what it does quickly is its architecture in a way. So just very quickly, this is kind of the high-level overview of Vespa. So whenever you create a Vespa application, you write a application package containing all the different kind of configuration components, your machine learning models, ranking expressions, and so on. And then we have a configuration system which pushes your configuration out to all the different nodes which run all these different services. And then when you update your application package, you can do that on the running system, and it will deploy the new version of your application without service interruptions. On the kind of query side, we have 2 kind of specific types of nodes. The container node, this is the stateless node where you can add your own code and so on. And then we have the stateful layer, which is the content nodes. That's where all the content is. Vespa takes care of distributing the content over all these content nodes that you have. And these machine learning models that you have, or these ranking expressions, they're automatically pushed down to all of these content nodes, meaning that that's where the computation happens, right? So you don't have to have like an external model server for a TensorFlow model, for instance, and then push all the features of all the documents to that external machine. That's very slow. Instead, we just rank it directly on the content node, which also means that if you need more performance, you need to scale up, you need lower latency, you can add additional content nodes, thus distributing the workload over a larger number of nodes as well. I'm going to drop this for the interest of time. Or just really quickly. the way that we handle machine learning models in Vespa is that we don't have like TensorFlow runtimes and so on going in the background, but we convert it to our own internal ranking expression language, which is optimized fairly heavily. So it's easier for us to add additional support for additional tools as well. The deployment strategy that is used here is that we have an experimental bucket. That's where this reinforcement learning is going. It's a small bucket which is where this kind of hourly updating a model happens every time, or happens all the time. But we don't have that in like full production because we want to protect the users, protect the system a little bit. So every so often, this model that's running inside this experimental bucket is frozen, and it goes through an A/B test to compare it with the production model. If that passes, it goes to the production model and works then. So the results, I was going to show a nice graph here and so on over time, but I wasn't kind of allowed to. But the kind of end result was that this was about 25 increase in time spent. So it was a fairly successful project. And going forward, we're experimenting with more features for larger neural networks, personalized comment ranking, and more sophisticated rewards, right? Because right now the only reward is increased time spent. Right? And that's a very singular objective. And if you don't have other things in place, then you can think maybe the community evolves into this type of discussions which engage a lot of people that could be very nasty. So you need some other kind of signals as well. So that's something we're experimenting with. Just to kind of lastly, is that while what I've been talking about is about comment ranking and so on, we created this system around this, then it's totally generalizable to the kind of system where we have some sort of machine learning model that ranks stuff and evolves over time. So this kind of implementation or this kind of system that we create can be generalized to other types of applications as well: search, recommendation, ad selection, query answering systems, and so on, such as tech support and so on. Yeah, we're a large set of people that were actually involved in this project, not only us at Vespa, but we had different teams. This was a cross-functional, cross-organization project. That was all. Thank you.
Thank you very much, Lester. Right, we do have some time for some questions, and get a T-shirt for a question if you haven't already got a T-shirt. Yes, the man at the back. Desperate for a T-shirt. You wanted the mic? You can't keep the mic. You can keep the T-shirt. Would you like the T-shirt? Okay.
Hi, awesome talk. Thank you. I was curious. I'm not sure if this you didn't touch on it, but I'll ask. So, in the index structure that Vespa maintains, for example, in Lucene, apologize for mentioning it, we have doc values, for example, which are used for custom sorting and scoring and all of that stuff. But then we also have in the posting list, we have at the positions we have payloads which are arbitrary and they're kind of unwieldy. So, however, this is these are places in the index where you're putting extra information that you can use for customized score features or whatever. So how does that structure compare to how Vespa stores it inside the inverted index?
Yeah.
And make it available.
So inside Vespa, we have these search definitions. That's how you kind of define your schema in a way. And each document has a set of fields. And these fields have different attributes or different kind of settings that you can set upon them, right? In Vespa, it works like so that different sets of these settings enables you to search for them, right? So the matching part. But then we separate very clearly between the ranking or the matching part and the ranking part, right? So the ranking part is defined by these ranking expressions, And there's this language that we use, and you can use a lot of different ranking features, and we have this expression language where you can combine them in any way that you want to. When it comes to matching of these features, they need to be like, you have to set some sort of different features, so they have to be in the memory and so on. But they're also inside the index structure. There are also many kind of hidden features as well that we use for different ranking features, such as like so this word appears in this document at this position and so on. Those are typically features that is not available for you as a user, but are used inside of these different ranking functions that we use as well. So, yeah.
Okay, I think we had another question that was around here somewhere. That's the man.
So hi, thanks for the talk. It was very interesting. I just wanted to know, for example, I'm used to use Lucene, Solar, and Elasticsearch. That's well, I know. Is Vespa AI like completely comparable to any of those? Like I'm just doing an e-commerce search or something like that. Can I use it or?
Yes, definitely. I tried to get the impression earlier on that it can be used for a lot of different things. But yes, e-commerce, we have a sample app, a use case sample app out for a kind of a shopping site as well. So you can just go online, check the different tutorials and that use case. So yes, that's a very common way of using it, yeah. Mm.
Okay. René, would you mind? Yeah?
Thank you for your talk. Very interesting. I have a question on how you handle, for example, long comments or new comments in the ranking. Because, I mean, for dwell time, it would seem that long comments would influence it more than short comments. And the new ones, how they manage to pop up when you have 10,000 comments.
Yeah. So taking the last one first, there is how new comments have can pop up after a while. So basically, this is the sampling method, right? So no two persons see the same order of these rankings, and if there is also another thing is that it's the features of the comments that are ranked, right? Not the comment itself, right? So if the features to the comments say that it should be ranked higher, then it will be ranked higher, not necessarily the kind of comment itself, right? Okay. So in that way, the sampling method ensures that comments that might have been kind of ranked fairly lowly, it has a chance of over time being ranked highly if the community spends more time on those kind of comments. Okay, and also I believe, I'm not entirely sure, but length is normalized in here somewhere, so the length of the comment shouldn't be too much into consideration.
Okay, thank you for your talk. It appears to me that the frequency at which you deploy your models is quite high. So is this something inherent to reinforcement learning, or is it just because you can?
Good. Well, it is inherent to reinforcement learning, right? Because you want to kind of capture the movements of or the dynamics of the community shifting interests in some way. So you need to be able to capture that in a way, right? But also because we can, I guess. There's different ways of deploying models in Vespa. One is deploying the entire application anew, because the model is a part of the application package, and that's a kind of a little bit more heavyweight process. I didn't show it, but in this particular application, what they did was to kind of deconstruct the parameters of the model and feed that in as a document. Meaning that this kind of weights for this model was actually a kind of a document inside the system. And inside of Vespa, we can have like document relationships as well. And this was used as a kind of a global document and so on. So this means that we can kind of switch models instantaneously, because it takes only a few milliseconds to feed a new document as well.
Right. Thank you very much, Lester.
Thank you.